I'd like to continue our discussion of Laplace's equation, and in particular using the method of separation of variables in the Cartesian coordinate system. Last time we developed how to get a solution for a particular problem in 2 dimensions, and we will continue that discussion looking at what these solutions look like. Let's review the problem that we're working on. Remember, it's a channel that goes to infinity in the x direction, so from 0 to infinity in the x direction. It goes to infinity in the plus or minus z direction, and then at x equals 0, along this plate right here, we have a potential v0y. We're taking a very simple case where this is a constant above 0, and then it drops to 0 as soon as you go over onto these other plates. So this is what the potential looks like on that plate. So starting at y equals 0, it jumps up to v0, it stays constant until it gets back over here at y equals a. So we're talking about going right along this line here where we have a constant potential. Let's go back and construct the series for the full potential as a function of x and y. And this is valid for x between 0 and infinity, and for y between 0 and a. And remember, it's independent of z. So we have then the full solution, which I wrote in terms of c sub n's, and then I put in the c sub n. So this is the potential. Here's the story. This satisfies Laplace's equation. If you don't believe me, put it in. And it satisfies the boundary condition. And from the uniqueness theorem, that means that this is a allowed and suitable solution for the problem. So what I'd like to do is look at a little more plotting in terms of the functions that we are using here. So I'm going to go to Mathematica. So here's our function, and I've got an n max equal to 200. Here's our v of y. This should be v0 of y. So that's right here. v0 in this case is just the amplitude of that function up here. So this is v0 here, and I'm going to set that equal to 100. So we'll plot it. Took a little time because there's so many terms. 200 terms is a lot. If you go back to 2, it looks like that. Adding the 200 will give us a better fit, as I said. And you can see the wiggles a little bit better here in terms of the endpoints. What I didn't emphasize is that this is a periodic function because we have these signs in this series. So the sign as a function of y keeps going in a wiggly form. And so let me just plot that. Look what it does. So I plotted it from -1 to 1, and this is what it looks like. It's like a sine wave, and so let's see, if I go up here and put in 6. Okay, so there's our wiggles. Now we go here, and we see the wiggles. But this function here is a repetitive result, and so now I'm going to go y equals 10a and 10a here, and you can see the periodicity. So given that we have a Fourier series for the v0, which is the value of this function here at x equals 0, we can generate the whole function. And so we'll take the Fourier series and put it back into the equation for the full potential. Using the coefficients that we derived for the Fourier series, that's this factor right here divided by this factor here, where the m dependence is just down here. Here's our x dependence right here, and here's our y dependence right here. Let's take a look at that. We'll plot this. But before that, we're going to take minus the gradient, and since this is a xy dependent function, we take it with respect to x and respect to y. So those are the partial derivatives. We're also going to find the magnitude of the E field. This is the E field. I called it Grady, but it's really the E field because of the minus sign. We're just going to take the magnitude of E, which is going to be what's called the norm of this vector here. It'll find the norm of the E field, and that's the same thing as the length or magnitude of the E field. We have to pick parameters, so we're just going to let a equal 10, b equals 20, and v0 is equal to 100. So I've run this already, so here's the 3D plot of this particular function, v of x and y, where this is the x direction here, and this is the y direction. This is the y direction. This axis is the potential. So if you look at x equals 0, then you can see that this function is very close to a square wave. It goes up, it goes across, and then it comes down again. The point that it has wiggles up here just has to do with we have a finite number of terms. I chose 80, so you see the 80 up here. Then let's look as we increase x, then what you see is the dependence on x should fall because of this exponential. It's an exponential minus something. Realize, however, that that x dependence depends on the summation, so it won't be a perfect exponential, but it'll be due to the sum of all these terms. Given that, if you look as you go out in x, eventually this looks like it gets to 0. It doesn't really go to 0. I can show that by just taking this range, so let me just take b equal 2. So we're going to go way down here and look at that. Okay, so you can see that it's still hanging up here, and so then let's go to 5, and it's still hanging up here. And now what I want to do is blow this up in terms of the sensitivity in this direction. Actually, I'm going to take this out to 20 again, where it was really flat. So I'm just going to take this down, and so I had 100. Let me take it to 5. We're way off scale in this region here, but notice that we still have amplitude at x equal 20. So this really doesn't go to 0, and you realize that if you had just a simple exponential, it would go very, very far, as long as you're willing to look for very small numbers. Going back to 100 again, then it'll be the normal plot. So it goes back to this, and we have our function that we started with. So two-dimensional function, this is v. This is how v depends on x and y. Remember where we're looking. This dimension here is into the channel, like this. And as we go further and further away, it goes to 0. This direction is actually in this direction. Okay, so let's generate a contour plot. So we already have this function, so we can take the contour plot of this, and let's see what that looks like. Here's the contour plot. What we're doing is taking slices at different values of v. So we're taking slices of this plot here as we change the value of v. And so up here we have high values. So we have very high values here as we go up towards the plate, and then this just falls and just keeps falling as we go down. Mathematica quits plotting, but there's more contours out here that would be even smaller. If we take a look at this plot here, this is about, what, 12. So we're looking at the curvature that is along this value in this vicinity here, and realize what we're doing is we're taking a cut at 3.2. So if this is 100, then it's very small. So you're down in this region here. So you're taking a slice of this through that potential. Out here you have a value of 3.2 that has a contour like this. Now I'm going to do a vector plot of the E field, what I call grady. As you know, vector plots aren't all that great, and the reason is because the magnitude of the vector is changing so rapidly as we go in this direction. Remember what this is, though. This is the slope of the potential with a minus sign. So if you look over here, the slope is negative as you go down. The slope is highest right here, and then the slope gets very, very small out here. So that's why the E field is large here and then gets very, very small. And this is, remember, the negative of the slope, and so therefore it points in the positive direction, since it's changing most in the x direction. Around the edges, of course, it's curling because of the fact that it has to be normal to the contours. So the E field follows lines that are very close and intense right here. Out here, you have a vector like this, and then here you have a vector like this. Well, it's easier to see the stream plot. We've done this before. Let's run that, and again it has to take the gradient again. I'm going to plot the streamline on top of the contour. So here's the streamline plot. Here's those corner vectors, and it's deceiving because these are equally spaced. They're not related to the intensity. Coming down that slope right in the middle, you have this fairly uniform direction. Well, in fact, it has to be, because it has to stay normal. And so here's the deal. You have your contours like this. Your streamlines will always stay perpendicular to the contours. This would be the way that if you let a particle go or zero velocity, it would tend to try to follow the field lines. So here it would just whip around. Way out here, it would go in a straight line this way. Given these plots that we've already shown, here's the potential versus x and y, and here's the E field. Let's take a look at the potential and E field magnitude right down the center of the plot. We're staying at y is a over 2, so this is y, and so we'll go down the center, and we'll just go along here and plot the magnitude of the E field and the magnitude of the potential. And so that's this plot here. You see here the potential, which falls as we would expect, so we're coming right down here looking at the magnitude of that function. And then here is the magnitude of the E field. And I think you can see that it actually peaks at a value not equal to the x equals 0, and it has to do with the slope of this function. We might be able to see that if I expand this a little bit. Okay, so you see this exponential type behavior gives us a very small change in v. So therefore the change of v, which as a function of x is the E field, and so this is very small. And so then as you go up, there's a little bit more curvature, and so this builds up. Let's look at the magnitude of the E field as a function of x and y. What I've got here are these plots. I've taken two scales for the coordinate here. One is going to 75 and one's going to 100. This one here is substantially adequate for what we want, and what I wanted to show you was at the corners you have very large magnitudes of E, versus out here where the potential is close to flat, you have very small E fields. So in the corners, very high, and then out here. And then you might notice that this valley here is fairly small, because again the potential is not changing very rapidly. So if I go back into the contour map, what we're talking about is the intensity of the E field over here versus over here, and you can see that the spacing of the contours is smaller than it is over here. And then as you get out here, the potential is changing very little in this direction, say, and so therefore the magnitude of the E field goes to very small values. So we can blow this up a little bit by going to a very small value of the potential axis, and let's take a look at that. And so what I show you here, letting it saturate at the smaller values of x, then you see how this is changing, which is the E field now. The E field is still falling as we go out, and notice that it's not equal to 0 at this value of x, which was 20, the maximum that we had there. If you consider then the fact that the potential is not 0 and it is still falling, you get a non-zero value for the E field.